Okay, it looks like we've got a red light. I think that means we're recording. Welcome to week 5 of CSE 142. Normally, I would be letting you know that we have a midterm coming up next week, but as I said at the beginning, we're not doing exams this quarter. The 143 instructor and I talked about this a little bit. You know that there are different options we could have pursued. Maybe we'll do the later assignments earlier, you know, because we could just kind of keep going at the same pace. Maybe we'll do an extra assignment or something. And we decided that given everything that's happening this quarter, that it kind of makes more sense to give you a bit of a break. So there's going to be a 5th homework assignment that will go out on Wednesday, and it'll be due next week. There won't be an assignment going out next week. So we'll have kind of a week in which you don't have to be working on homework. There's going to be some things we'll do in section that we think help to reinforce some of the things we've talked about. I'll say a little bit more about how I think it might be helpful to you to kind of review some of the midterm material, even though you're not going to take a midterm. But you have a bit of a break, you know, and then we'll kind of follow the schedule as usual, starting with a homework that would go out the week after that. So there's going to be a week where you don't have a homework to work on. And we think that's a good thing to give you a bit of a breather to get ready for the last few homeworks. Let's see, the question of the day last time had to do with your preferred operating system. Lots of people with Macs, apparently. Windows, still more of those. Not very many people using Linux. So that was an interesting set of responses. So let me switch to Java. So as I said, we're moving into material that'll be for the homework that I pass out on Wednesday. Keep saying pass out, that I make available on the webpage on Wednesday. And it involves chapter 5 material, and we're going to do some of that in today's lecture. So the first thing I wanted to talk about was a certain kind of a loop. This loop is something that we could have talked about before, this kind of loop that I'm about to talk about. But, you know, it seemed to make more sense to throw it in chapter 5 when we're kind of talking about lots of issues related to various loops. So the idea would be, suppose I'm going to call a method print numbers, and I pass it a number like 10. I want it to print 1, 2, 3, 4, 5, you know, et cetera, up to, 9, 10. I want it to print the numbers 1 through 10, with commas. That's what I want it to do. So we can make a public static void method called print numbers that takes a parameters that I'll call, say, max. So this is pretty standard chapter 2 stuff. That we could do a for loop for int I equal 1, I less than or equal to the max, I plus plus. We can do system.out.print of I. We want to print those numbers, 1 through max, and then a println that would complete the line of output. So that's kind of a first version of it. Let's go ahead and compile and run. And it does print the numbers 1 through 10, but they're all scrunched together because I use simple print commands. I mean, I do want them all on a line, but I want them to be separated. I want some spacing, I want some commas and so forth. So I normally ask, what do we do? And somebody kind of suggests, well, you need to concatenate, at least a space, and actually we need more than the space. We want a comma and a space. So we don't want to just be printing I. We want to print I with a comma and a space. So let's go ahead and compile and run that version of it. So that's good in that, we got the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The only thing that's not very good is we've got a comma at the end. So whoever suggested that, that we concatenate the comma and the space was wrong, that what we should have done is we should have had a comma and a space up front so that way we don't end up with a comma here at the end. So I can go ahead and compile and run. And great, we got rid of the comma at the end, but now we have a comma at the front. Well, so maybe we really need it at the end, we need it at the front, we need it at the end. I think you can tell, neither of those approaches is going to work. This is a kind of problem that's known as a Fencepost problem. So this is kind of a well-known situation that comes up in programming. You'll encounter a lot of Fencepost problems in the code that you write. Normally I'd be telling you that on the midterm, it's likely to come up. But in general, it's good to know about this anyway, because very common situation, you want to know how to fix it. So here's the analogy. Suppose that I was going to put up some fencing, and I was going to say do 100 yards of fence, and I wanted to have a fence post every 10 yards. So how many posts do I need? Well, if you did a quick calculation in your head, 100 yards, every 10, so 100 divided by 10, you need 10 fence posts. But that's not right. You actually need 11. Probably most of you got that right. But so you put down a post, and then you have some wire, and some post, and some wire, and some post, and some wire, etc. Post and wire. And so you begin with a post, and then have some wire, post and wire, etc. But if you end with wire, then you've got kind of this dangling bit of, wire at the end of your fence. You're going to want to end with a post. So you begin with a post and you end with a post. That's where this name comes from. That's what's special about it. And here's a way of thinking about it, is that what you find with all of these fence post problems is there's something that you want to do n times and something else that you want to do n minus 1 times. Or the other way around. You could think of it as, there's an extra one, or that there's, one that's missing. But we would want 11 posts, but only 10 sections of wire. So that difference of 1. So an extra post relative to the amount of wire. And so what are we doing here? We want to print out 10 different numbers, so that we do want 10 of them to be printed, but how many commas? How many commas do we want to print? Only 9. So there's kind of an extra number relative to the number of commas. So in the fence post analogy, the numbers are like the posts, and the commas are like the wire. So how do we do that? It's sad that I don't have an audience, because this is always fun to hear various suggestions that people have. There's lots of different things that people come up with. One of the most common answers that people mention is, what if we did system.out.print, of a 1 before the loop begins? So what if it's like planting a post. So what if we do a 1 before the thing begins, and then instead of having the loop start at 1, we have it start at 2. So we do the first one kind of manually outside of the loop. We plant, we print the first number, we plant the first post outside of the loop. And then you'd have to make sure that what you're doing inside of here is the right order. And actually this is the right order if you think about it. What you'd want to do is, if you did the very first post outside, then what you'd want to be doing in your loop is wire post, wire post, wire post. And that's kind of what we're doing here, is comma number, comma number, comma number. So we print our first number beforehand without a comma, and then in our loop, comma number, comma number, comma number. So let's see what happens when we compile and run that version of it. And now we've got our 1 through 10 and no extra commas. So the loop prints 9 numbers with commas, and the 10th number gets printed before the loop begins. So that's one solution to it. I'm going to make a copy of that, and let's see. Let me just kind of comment out that particular solution right there, and then let me paste in what we had so we could kind of change it a little bit. So I usually ask, does anybody have another suggestion? And people usually kind of realize, well, if you're going to do one of them outside the loop, you can do the first one outside the loop, before the loop begins. That would be fine. But another thing to do would be to let the loop start at 1 the way we'd intended, but we let it go to max minus 1. So we end the loop 1 early, and then what we do is to do the max here. So what we're going to do is we're going to do post wire, post wire, post wire, and we're going to do the final post by itself after the loop is done. And if we do it that way, then we've got to switch the order in which we're doing this, because now we really do want to do it kind of in that other order where you're doing number, comma, number, comma, number, comma. So we do that 9 times, number, comma, 9 times, and then we get the 10th number through the println. We do that one kind of at the end, after the loop. So we can compile and run that version, and we're getting the correct output again. So those are a couple of different ways of solving the fence post problem. I would say that the more common one that people use is to do something before the loop begins, but sometimes it's more convenient to do the last one after the loop is done. So it kind of doesn't matter, either, whichever one is easier, you could do. They both work fine. There's another solution that I wanted to at least mention, and normally if I asked, there'd be at least someone who would realize that this is something that you could do. What we could do inside the loop is we could always be printing the I, but we could use an if to decide whether or not to print the comma and the space. So it's conditional execution. We don't always print the comma and the space. We do it most of the time, but not on, say, the very first iteration or the very last iteration. So that's another way to go, is to have kind of an embedded if inside the loop. I'm not a fan of that particular solution because the test that you would use is repeating a test that we're doing in the loop itself. You really only do it once. Most of the time you aren't doing it. So an if isn't really the most appropriate thing. Although, depending upon the code that I'm writing, I could imagine a case where the if would make sense. If you're trying to avoid, say, a lot of redundancy or something, it might be worth doing. So these are the two most classic solutions that I would recommend you be familiar with, is handling one of the values before the loop begins, or handling one of the values after the loop is over. And notice how we had to kind of switch the order of the fence and the post, depending upon which of those approaches we took. Okay, so this is in the slides for today. This solution is in the slides for today. Both of these solutions are in the slides for today, and it's in the chapter as well. So I'm going to go ahead and get rid of that from main because I want to switch gears a little bit. So what I wanted to do next is I wanted to say, suppose that I had a number initialized to be 1, and I said while number is less than or equal to 200. Oh, excuse me. What I want to do first is I want to do an if. I'm going to say number equals number times 2. I was thinking too much about where I'm headed and not where I wanted to start. System.out.println number. So we're going to talk about a new construct, and I've kind of let the cat out of the bag a little bit, that it's going to be something called the while loop. We'll get there in a second. But I wanted to show you kind of the if version of it, because this should be more familiar. This is a chapter 4 type thing to do, is that you start out with a variable number that is initialized to 1. You see if it's less than or equal to 200, which it is. So you'd set number to be number times 2. So you double it. And so it's not surprising that if I compile and run this little program, that it prints out a 2, that it doubles that number to be 2, and it prints it out. I jumped the gun a second ago, but so what I want to talk about in today's lecture, and we'll do more in Wednesday's lecture, this is a chapter 5 concept, is the idea of using a while loop. And one of the reasons I wanted to do it this way, where I use the if and then I switch to a while, is just to point out to you that the syntax of this new construct is very similar to the syntax of the if. It really is just a replacement of the keyword. So a simple if has the same kind of structure as a while, but it has a different property to it. So if I kind of compile and run this version of it, it prints out 256. So a very different answer, not 2, but 256. I think it'd be helpful to try to see what's going on here. I'm going to throw in a system.out.print, and I'm going to print number plus a space. So as I go, I'm going to we'll see the initial 1 that it has here, and we'll kind of see the different values that it takes on. So I'm going to compile and run this version of it. Look, there's a lot of different values that are printed out. So initially number was 1, and then it got doubled to 2, and then it became 4, and then it became 8, then it became 16, until it finally became 256. This 128 was printed by the print that's inside of the loop. Then we doubled it to 256, and the final println printed out the final value, the 256. And so you can see that it did this many, many times. So the English of it, I think, implies that pretty strongly. While this is true, keep going. So not just once, but potentially many times. And as usual, there's a nice slide in today's slide deck for this. So this is a slide about the while loop with this particular little example. And it kind of shows you in the railroad diagram here. Remember what we had with the if was that it performed the test, and if the test evaluated to true, it executed this code once, and then it went to this code that came afterwards. Not here. We come back around and we do the test again. So it goes around and around and around and around, performing that test over and over and over again. And as long as that test is still evaluating to true, it keeps executing the body of the loop. So that's why it's a loop, not a simple if, that it can execute it many, many times. And only when it fails does it kind of exit here. And on the slide, it has very similar code where it's printing out the num and the space. It didn't have the final println we had, and that's why it ended with printing a 128, because it didn't print the final value that num had here. So that's why we have one extra number relative to that little example from the slide. Well, that's the idea of the while loop. I think that an interesting thing is that the syntax is pretty simple for a while loop. The concept is not that complicated. That's kind of not what people struggle with. What people struggle with is using it well. And we're going to see this, that there's, particularly in the last example that we're going to do today, we're going to see something where it turns out to be hard to work out the logic of what we're going to do. All right, so that was again in the slide, so I'm going to get rid of that example right there. And I want to do a different example with you. I want to talk about a Sentinel loop. Sentinel loop, it's a special kind of a loop. We're going to be doing user input. So I'm going to have a scanner console, which is a new scanner connected to system.in. And I could try compiling the program and let it fail, but I think you guys are probably used to this by now, that you know that if I'm going to use scanner, I have to have import of java.util.star for it to know about the scanner. And so the idea is that I want to read in a series of numbers and add them up. And I'm going to use a special value, what we call the Sentinel value, to kind of signal that I'm done entering values. So we're going to be doing a cumulative sum. Remember the form that the cumulative sum took. Int sum starts out at 0, and then some kind of a loop. Initially we were doing for loops, but now we're going to be doing while loops. So some kind of a loop. I don't know yet what the test will be. And inside here, we're going to say sum equals sum plus something. And then after the loop, we can use the sum. In this case, I just want to print it out. System.out.println sum is equal to, sum is equal to sum. This is just, what I've put here is just the cumulative sum pattern that we talked about in an earlier lecture. So I'm going to want to do something like that. What I want to do in this case is I want to be prompting the user, system.out.print, say something like next int -1 to quit. And how about if I did that like that? And then I'm going to say int number equals console.nextInt. So I'm going to prompt for a number and read it in. And then I can use that number to add that to my cumulative sum. So that's what I want to do, the kind of the work I want to perform. And as it implies with the prompt here, I'm using -1 to be a special value. So I'm not going to be able to add in a -1 because -1 is the Sentinel. -1 is the one that indicates we're done. So this is not an uncommon pattern that you might use where you enter, and then you enter some special value that means we're done. Maybe you don't enter anything at all. You just hit an enter key or something, and that means you're done. But in this case, we'll do a -1. So one of the questions then becomes, what do we put here for the test? There's some interesting research that psychologists have done where they've looked at novice programmers, and they found that novices find it easier to reason about why you would exit a loop rather than why you would why you would continue a loop. So, but the while loop isn't done that way. The while loop tells you why you continue, not why you exit. But if you want to think about why would you exit, well, you'd exit because the user gave you a number that was -1. So, a number equal to -1 would be the reason to stop. But the while loop is a reason to continue, not a reason to stop, so we have to give the negation of that. And you may remember I mentioned the idea of relational operators, that there's a bunch of these. They're mentioned in a table in chapter 4 and in the slides for when we first did if, but not equal to. So number not equal to -1. So that's a relational operator that's testing whether something is not equal to something else. So that's, we'd want to continue going while number is not equal to -1. So I would say that there's some good things about this logic here. That we've got the cumulative sum pattern, we've got kind of the right test, I think. But this is not going to work out. This is problematic for a bunch of reasons. If I compile it, the compiler says it cannot find number. What do you mean you can't find number? Well, this is a scoping issue. This is a case where you're going to find while loops are not always as convenient as for loops are. With for loops, we had that rather complicated syntax, but in the header for the for loop, you could introduce variables that were used inside of the for loop. That's not true in a while loop. So here, the way that we introduced number was we declared it here. Well, what's the scope of that? What's the scope of that declaration? Well, we'd want to look to the curly braces that contain that. So take a look at the curly braces that contain that and the lines of code then that contain that, and you can see that the test is outside of this scope. The test on number here, this is not within that scope. So we're going to have to declare number outside the scope in order for that to be able to work. And that would mean we don't want to declare it here. You can't have it twice. Java won't let you declare that thing, have two of them. So we would not declare it inside, we would declare it outside. So this is going to solve the scoping problem, but we still have a lot more problems to deal with. So we can compile, and now it says variable number might not have been initialized. Well, so now what it's saying is, well, look, you've introduced this thing called number, but you never told me what it's equal to, and now you're testing. You're testing to see whether it's not equal to -1. This is a problem that we sometimes refer to as priming the loop. Sometimes, it's like priming the pump, getting things started. Sometimes we have to kind of put in a special value for this loop to get it to begin the loop, to start that loop to begin with. So we want to set number to be something. There's lots of things we could set it to. What would be the dangerous value to set it to? -1 is actually the one really bad value to set it to, because if we started number at -1, then we'd never go inside the while loop. So it wouldn't get us into the while loop. So we could set it to something like 0. Anything that's not -1 would be fine. We set it to something that's not that, and that allows us to go into the loop. So let's see. Now we compile properly. How about what are we going to add up? How about 3, 5, 4, and then a -1? So let me see. 3 and 5 is 8, and 4 is 12, so that adds up to 12. Maybe my math isn't so good. 3 and 5 is 8. 8 plus 4 is 11. Doesn't sound right. I think you can see what's going on. It's adding in the -1. And we don't want it to add in the -1. So that's the problem here. So if you think about it, what are we doing? We do a prompt and read. That's kind of a pair of things that we do together as a step. And we add something into our sum. Prompt and read, add it into our sum. So here, how many numbers do we want to do a prompt and read for? We want to get 4 numbers. We want to prompt and read for 4 numbers. How many do we want to add into our sum? Only the first 3. So this is a fence post. This is a classic fence post type situation. So what I'm going to do is a classic fence post solution. So I'm going to take this initial prompt and read, and I'm going to copy it, and I'm going to put it here. I'm going to do the first prompt and read before the loop begins, And then I don't need to do this anymore because now I can just set up number because of the first prompt and read. But now if I'm going to do, like if you're doing the first post before the loop begins, then remember you have to reverse the order of the things inside. Wire post, wire post. So I'm going to want the sum, so I'm going to want to go ahead and cut this from here. I'm going to want the sum to be first. So I do two things to follow the Fencepost pattern. I do the first one before the loop begins, and I switch the order inside of the loop. So I plant a post outside, and then I do wire post, wire post, wire post. So that's kind of what I'm going to do. Let's go ahead and compile and run. And so let's try our, what did I do? 3, 5, and 4. And we do a -1. And now they add up to 12, which is what we were looking for. So that's kind of the Fencepost solution to this. Often I say, are there any questions? And this example is simple enough that there are some interesting ways of avoiding the Fencepost solution, of kind of doing something other than the Fencepost solution. But let me just say that I don't want to talk about those other solutions because they're not general purpose. They won't always work. Marty Stepp, when he used to give this lecture, got so tired of people seeing these other ways of solving it that he stopped using this example and instead used an example that involves strings. It's in the slides. I recommend you take a look at it. That string example requires that you do it in this kind of way, some kind of a full Fencepost solution where you do the prompt and read outside the loop. So you can look at that. I mean, I wanted to show you a general purpose solution that works in all cases, even though there are kind of some ways to simplify this code a little bit in the numeric case. So if some of you are kind of saying, but couldn't you, the answer is probably yes, but we want a general purpose solution that works for everything, including Marty's string example. So check out the slides. It has both of these, this numeric problem and the problem that involves string processing. And you'll see you really do need a Fencepost type solution for that string one. Okay, well, so normally I would let students ask questions, and there might be, lots of questions that they would ask, but I think I'm going to go ahead and move on then. So this is kind of the Sentinel loop example. I want to revisit a problem that we looked at before, and this one is going to turn out to be an interesting one in terms of trying to get the correct logic for something. So remember, when we were first looking at return values, that I had a little method called 2days that did a computation. It would divide milliseconds by various numbers to convert it into a number of days. We were calling the system class's current time millis method to find out how many milliseconds have passed since January 1st, 1970. That was kind of this day that's known as the epoch. So if I compile and run this version of it, what it tells me is that this is how many milliseconds have transpired since then, and this is how many days have transpired since then. Well, I want to do a computation with you that would be a little more interesting to us. So I'm going to say that int year is 1970. So we know that this was all relative to a year of 1970. And I'm going to say that the day is kind of this thing that we got from the days. So I want that in integer form. So I don't want 18379.7, I want 18379. And so remember, I can use casting. I can cast to an int that variable called days. So this is a cast that says, turn that double value into an int, and it does it by chopping off, the decimal part. So we're going to get an 18379. And then here, I'm going to have it say system.out.println year is equal to year, and system.out.println day is equal to day. So let's go ahead and compile and run this version. And it says that today is day 18,379 of the year 1970. That's not what we want to end up with, but it's not a bad starting point. Before I do that, I want to mention a minor fix here. I'm recording in the morning. In fact, you can probably tell from my Mac it's around 10 o'clock in the morning. And notice what it's saying for days is that we're 0.708 into the day. We're 7/10 of the way into the day. That's not true at 10 in the morning. So why is it saying that? So I normally, anybody know why would it be reporting that? Well, the current time, millis, is reported relative to Greenwich Mean Time. So that's not our time. We're in Pacific time. And I will often ask people, do you know how many hours off we are? Turns out that we're 8 hours off from Greenwich Mean Time in general, which is about a third of a day. So I'm going to subtract 1.0 over 3.0. I'm going to subtract a third of a day to account for that. Gets us somewhat, mostly right. You'll see now it's closer, 0.375. If you do a very careful computation, you'll find I think it's still off by an hour because it's daylight savings time. But let's not worry about daylight savings time. Let's just kind of, that's close enough that we're getting a pretty good computation there. Here's what I want to do, is I want to be able to figure out that it's 2020. So I want it to tell us that this year is 2020. And I want to know what day it is this year. So what day of the year is it? And I have in mind that, January 1st is going to be considered day 1. January 2nd is day 2, and so forth. So what day is it today? It is April 27th. April 27th. So let's see. How many days then have gone by so far this year? January, 30 days, September, April, June. And so I think there's 31 days in January. How many days were there in February? 28 days in February, 28 normally, but this is 2020, right? So this is a leap year. So we had 29 days in February, 30 to now March, 30 days, half September, and so forth. So 31 days in March, and today is the 27th. So we're in day 118. So I'm going to want it to tell us that, that we're in day 118. I'm going to want to have it get to the point where it reports that to us. So that's what it's going to tell us. It's kind of what year it is and what day of the year is it today. That's our task. All right, well, let's talk about a few cases. I'm kind of creating a little comment region here for myself so I can type some things. Remember, you can use these special characters to do a multi-line comment block. So what if the day, say, was 285? So what if, when we ran this program and we got a value for day, we found that it was 285? Well, that would be really easy, right? We would basically say there is a day 285 of 1970. We would say that's okay. That's an okay value for day to have, that it's 285. What if when we ran the program, day had the value 465? Well, there is no day 465 in the year. So what would we have done here? We can account for a year by kind of moving the year up to 1971. So we can bump the year up by 1. And then there were 365 days in 1970. So wouldn't day become 100? This would kind of require one adjustment where we go up a year and subtract 365 days. What if day had been 765? Well, then we could have said, all right, there was no day 765 of 1970, so we'll advance it to 1971, and it would be day 400 of 1971. Well, there's no day 400 of 1971, so we'll advance it to 1972, and what day is it of 1972? We take away 365 days. We'd say that it's day 35 of 1972. So that's the kind of thing that we want to do, is we want to kind of adjust year by year by year until we get day into a reasonable range. Not surprising that since today's topic is while loops, that we're going to have some kind of a while here. And what was I doing when I do an adjustment? I was increasing the year by 1. So we're going to want to say year plus plus. And I was decreasing the day by the 365 days that were in that year. I'm kind of accounting for 1 year's worth of days. So I'd want to set day to be day minus 365. So that's what I kind of want to do over and over again, is go to the next year and subtract 365 days from that year. What do I want to do then for the test? What are legal values of day? I mean, day of 765 was not legal, day of 400 was not legal, but day of 285 was, day 100 was, day 35 was. We're trying to get day to the point where, I mean, what are the legal days of the year? I mean, you can have up to 365 days in a year, right? So what we're going to want to say is, while the day is greater than day 365, we'd want to keep doing this. If you say it's day 10,000 or something, clearly we're not done. We've got to do adjustments. So we want to keep going. As you know, there was that experiment I mentioned the psychologists had done. We're trying to get to a point where day is less than or equal to 365. That would be the reason to stop, is if day became less than or equal to 365. But that means that day greater than 365 is the reason to continue. So let's compile and run this version of it. And it correctly figures out that we're in the year 2020, and it says that we're in day 129 of 2020, which I don't think is right. So what did we say up here is that we were going to be in day 118. So how did we get to day 129? What's going wrong? It's off by quite a bit, actually, quite a few days there. Well, so 1970, what we did, to account for that particular year, we would subtract the 365 days, 71, 365 days, 72. Were there 365 days in 1972? Turns out that 1972 was a leap year. So we got to do something different when we're dealing with leap years. So we basically need to say, if, leap year, then we want to do something different. And then else, the normal thing that we're going to do is to do this. But we'll do something different in a leap year. So how do you know it's a leap year? Well, kind of the simple version of that is that if year is divisible by 4, so that's kind of the simple test on it being a leap year. Well, I've mentioned to you before, Stuart loves mod. Mod is a very useful kind of operator. So if year mod 4 is equal to 0, so if we are in, the remainder when we divide by 4, if that's 0, that's a way of testing that something is divisible by 4. This isn't quite the rule that's used. There are special rules for centuries. So you may live to be able to tell people that the year 2100 is not going to be a leap year. So normally, every 100 years, every century is not a leap year. And I'm telling you, 2100 is not going to be a leap year. But every 400 years, there's adjustment the other direction where they are a leap year. So the year 2000 was a leap year. So for people my generation, my age, we didn't have to know a special rule. You are probably just about on the cusp there where you're likely to make it up to the year 2100, where you can tell all those young people that you learned in your computer science class that the year 2100 is not going to be a leap year. But anyway, for our purposes, divisible by 4 is good enough to see whether it's a leap year. So we would, again, kind of advance it, a year plus plus, but we wouldn't subtract 365 days. How many days are there in a leap year? 366. So we did a different adjustment for a leap year versus a non-leap year. So let's try compiling. And what did I do wrong here? Oh, I introduced the if-else, but I forgot to include a closed curly brace. So it was confused by what I had there, and that kind of absorbed part of the method that came after. And here we see it's telling us that we're in day 117 of 2020. 117. What were we trying to get to? We were trying to get to 118. Maybe we computed the day wrong. I mean, we could double check, or we could think this is in computer science what we refer to as an off by one bug, sometimes called an OBOB, an off by one bug. Somehow we've got something wrong here. Well, let me tell you why this is wrong. So think about it. It's telling us that we're 0.38, etc., into this day. Think of what would have happened if we ran this program on January 1st of 1970. On January 1st of 1970, if it was a little after 10 o'clock in the morning and we'd run this program, we would have gotten a number that's like 0 point some part of a day, some partial part of a day. But it would have begun with a 0 because we wouldn't have completed that first day of the year. But what do we want to describe January 1st as being? I think that the right convention to adopt is that we want to say that January 1st is day 1 of the year. Now, computer scientists, we kind of get used to things starting at 0. So maybe computer science folks wouldn't mind saying that the first day of the year is day 0, but that's not the way most people want to do that. Most people would want to think of that as being day 1. So we were kind of off by 1 to begin with, because it would have said that it would have said that January 1st, 1970 was day 0, when we really would have wanted it to tell us a number that's 1 higher. So we need to add 1. We need to add in, because there's going to be a partial day, and we're going to, in our scheme, we're going to think of that as a full day, because that's the way we like to think about it, is that January 1st of 1970 was day 1. So we add 1 to it to be able to do that. And we compile and run, and we get that it's day 118 of 2020. Pretty good. That was what we were looking for, is to figure out what year it was or what day of the year it was. Are we done? You might suspect that the answer is no. It's a little trickier than that. So there are special cases to think about. And so let me mention a couple. So I'm going to tell you that 12/31/19. That was December 31st of last year, and I'm going to say that that was day 18262. That's kind of what the day count was. This large number here, was that it was 18262 last December 31st. And let me give you a December 31st from a leap year. That the most recent leap December 31st. We're going to have a leap year December 31st this year, but that's in the future, so I'm kind of picking the most recent one from the past. And that was day number 17167. So here's what I'm going to do. We did a little computation up here to figure out what day is, but what I can do to kind of test things that are going on is that I can just manually set day to be something. So let's set day to be 18262. So I'm setting it to this number right here, 18262. I'm setting it to December 31st, 2019, and let's see what happens when I compile and run it. It tells me that it's day 365 of 2019. That's correct. December 31st was day 365 of 2019. Let me add 1 to it, just so that we see what happens for the next day. Excuse me. 2 plus 1 gives me 3. I can do math. So we'll compile and run this version of it. And it tells me that that was day 1 of 2020, which is correct. The day after was January 1st of 2020, day 1 of 2020. So far, so good. All right, let's go back here. And I'm going to begin, let me set it to 17166. So that was the day before December 31st, all right? The day before December 31st. And let me do a compile and a run here. And what it tells me is that that was day 365 of 2016. That sounds wrong, but it's not. Remember, it was a leap year. It had an extra day. So that meant that December 30th, the day before the 31st, the December 30th was day 365 of 2016. Well, let me go one above. So let's go to, instead of ending in 6, let's end in 8. So that's this number plus 1. So now what I'm doing is I'm giving it the day number for January 1st of the next year. So let me go ahead and do this and run. And it tells me that that was day 1 of 2017. So it got both of those right. It gave me December 30th of 2016 and said that was day 365. January 1st of the next year and said that's day 1 of 2017. But what about December 31st itself? So what if I set it to be up here, we'll set it to be the 7. So what if I set it to December 31st? And I compile and run. Well, first of all, let's think of what the right answer is. Last day of 2016, which was a leap year. There were 366 days that year. So that should be day 366 of 2016. It should be showing me day 366 of 2016. Instead, it's telling me that it's day 0 of 2017. It's moving into the next year, which is not right. So this is where things get really complicated, because there's all sorts of ways you could think of trying to fix this. But what's going on? So on that day, that 366th day of December 31st of 2016, it said that the day was set to 366, and it said that that was greater than 365, so it entered the loop. And it said it is a leap year, and so it's going to do this adjustment, and it subtracted 366 from 366, and it got 0. It turned it into day 0 of the next year. We don't want to do that. We don't want to kind of advance. On that particular day, on December 31st of the leap year, we don't want to do that. So I'm going to say that if day is greater than 366, I know that I'm in a leap year here. This is a leap year. So only with a day bigger than 366 now would be something beyond this particular year. So I only want to be doing this if it's a bigger number than 366, if it really is in the year after. Because those would, that would be like I'm back in a leap year like 1972, and this is a much bigger number. So of course I want to keep going by adding 1 to the year and so forth. Let me comment this out for a second just to kind of show you that if I compile and run this version, what it's reporting to us is that it's day 118 of 2020. So this is not causing a problem for us right now. This is kind of doing the right thing. It's saying there is a special case, when we're dealing with day 366, but for other ones, we would want to do what we normally would have done. And so it's working out, it's kind of giving us the right answer. But what does it do on that particular day, on December 31st of 2016? I'm going to go ahead and compile and run that version of it, and I'm going to see what I get as output. I'm going to wait for my slow computer and see what I get as output. Man, is it taking a long time to execute. It turns out that it's in an infinite loop. And there's a story associated with this. You guys are probably too young to have ever heard of the Zune player, but way back when Apple did their iPod music, player, Microsoft did their own, something called the Zune. Never quite took off, although some people who had Zunes. But the code for the Zune player included code like this to figure out what day of the year it was. And I have recreated a bug that was in their code. So what I'm showing you here is a faithful recreation of a bug that a professional programmer at Microsoft introduced into the Zune software. Look, it's still running, I have to hit N to stop it from running. It's in an infinite loop. Why? Day is 366 of 2016. It's the 366th day of a leap year. And I want to kind of be reporting that it's day 366 of that leap year. But what is it doing? It's saying, is day greater than 365? Yeah, 366 is greater than 365. Is it still a leap year? Yeah. Is the day greater than 366? No. So I don't want to go into the next year. I want to kind of stay at day 366. So don't do these lines of code. So then it comes back and it says, is the day still greater than 365? Yeah, it's 366. Is it still a leap year? Yeah, because I haven't allowed it to move forward. And is the day greater than 366? No. Yeah, no, yeah, no, yeah, no, yeah, no. It's going round and around and around. These 3 lines of code here, it's stuck in an infinite loop. And what actually happened is with the Zoom player, the real, true story, is that when we got to December 31st of a leap year, all the Zoom owners found that when they tried to turn on their Zoom player, it didn't work. It got caught in an infinite loop at the very beginning. Microsoft said, turn it off and back on again and it'll work. And it didn't. All day that day, it got stuck in an infinite loop, this infinite loop right here. It was only the next day, when we got to December 1st, that it fixed. The bug stopped manifesting. So, and it's tricky to figure out how to do this right. If those of you who kind of enjoy a challenge, I'm going to put this version of the code up on today's calendar, and I challenge you, try to figure out how to fix it. Try to figure out how to make it work right. I'll show you in Wednesday's lecture, my solution to it. But you might, you could download the code, play with it. You can set, the day to something like this, a specific number like that, and see whether you can get a fix. It's hard. It's actually not at all as easy as it sounds. All right, we'll talk about the solution to this at the beginning of next time. Thanks.